Hello guys, how are you? Welcome again to our lesson. Today we start section 3, equilibrium of acids, bases and salts. First of all, let us understand what we mean by ionization constant of a weak acid. The term Ka is called the acid ionization constant. Acid ionization constant, Ka, is constant for a specified temperature but has a new value for each new temperature. Acetic acid CH3COOH is a weak acid and most of the CH3COOH molecules remain unionized. An acetic solution contains CH3COOH molecules, hydronium ions, and acetate ions CH3COO-. So, as we said, acetic acid is a weak acid. That's why some of the acetic acid molecules will ionize and dissociate to hydronium ions and acetate ions, while most of the acetic molecules will not ionize. The equilibrium equation for the ionization of acetic acid is as following. CH3COOH plus H2O will form hydronium ion, positively charged, and the acetate ion, negatively charged. And the equation for Ka is as following. Ka is the concentration of the products over the concentration of the reactants. So it will be the concentration of hydronium ion multiplied by the concentration of acetate ion over the concentration of acetic acid. And here we can see that we didn't include the concentration of the water molecule. Why? Because water is the solvent and the molar concentration of water molecules remains constant. That's why there is no need to include the concentration of the water molecule in the equilibrium expression. So at constant temperature, an increase in the concentration of CH3COO- or the acetate ions through the addition of sodium acetate disturbs the equilibrium. This is what we discussed in our previous lesson, guys. Under the topic of common ion effects, we have here a compound called sodium acetate, and sodium acetate will ionize and it will release the acetate ion CH3COO-, and this will cause increase in the concentration of the acetate ion and will cause a stress on this side of the chemical equation. So this disturbance causes a decrease in the concentration of hydronium ion and an increase in CH3COOH, which is the acetic acid. Why? Because in order to reduce the stress, the acetate ion will recombine again with the hydronium ion and give us the acetic acid in order to re-establish the equilibrium. So the equilibrium is re-established with the same value of Ka, but there is a higher concentration of non-ionized acetic molecules and a lower concentration of hydronium ions. And as we know, the pH value of any solution depend on the hydronium ion. So any changes in hydronium ion concentration will affect the pH of this solution. So now let us discuss a little bit about buffers. What do we mean by buffer solutions? Buffer solutions resist changes in pH. Buffer solutions actually contains both a weak acid and a salt of this weak acid. For example, we have here acetic acid as weak acid, and the salt of this weak acid is sodium acetate. Buffer solution can react with either an acid or a base. When small amounts of acids or base are added, the pH of the solution remains nearly constant. So as we said, buffer solution will resist the changes in pH. To understand the mechanism by which the buffered solution works, let us have a look at this diagram. In this photo, the beaker on the left here contains a buffered solution and an indicator with a pH of about 5. The beaker on the right contains mostly water with a trace amount of acid and an indicator. And as we can see here, the pH meter shows a pH of 5 for this solution. So again, this beaker contains buffered solution while this beaker doesn't contain a buffered solution. So what will happen next, guys? Let us see. After 5 ml of 0.10 molarity, hydrochloric acid is added to both beakers. The beaker on the left doesn't change color, as you can see here, indicating no substantial change in its pH. However, as we can see here, the beaker on the right undergoes a defined color change and the pH meter shows a pH of 2.17. So as we said, the beaker that contains the buffer solution resists the change in pH value, while the beaker that doesn't contain a buffer solution shows a change in the pH value. So it didn't resist the change in pH. Now let us understand the mechanism by which the buffer solution works. First of all, if a small amount of acid is added to the acetic acid sodium acetate solution, which is the buffer solution, acetate ions from this buffer solution will react with most of the added hydronium ions to form non-ionized acetic acid molecules, as shown in this equation. So the hydronium ion that will form after the addition of the acid will combine with the acetate ion to form the non-ionized acetic acid molecules. This way, the hydronium ion concentration and the pH of the solution remain practically unchanged. The same will happen if a small amount of base is added. So if a small amount of base is added, the hydroxide ion of the base react with and remove hydronium ions to form non-ionized water molecules. Acetic acid molecules then ionize and mostly replace the hydronium ions neutralized by the added hydroxide ions. So again, the hydronium ion concentration and the pH of the solution remain practically unchanged. A solution of a weak base containing a salt of the base also behaves as a buffered solution. Buffer action has many important applications in chemistry and physiology. As we know, human blood is naturally buffered to maintain a pH of between 7.3 and 7.5. So that's all for today. Thank you guys and see you next lesson, inshallah.